Hey there, my name is Taylor, and today we're going to be looking at an electromagnetic induction problem. We are told that we have a magnetic field B directed upwards out of our page, passing through the given circuit connected to a 5 ohm resistor. We're told that the magnetic flux, phi sub m, follows this expression here in units of milliwebers, and asked to find the direction and magnitude of the induced current through our resistor at 3 separate points in time. So to solve this, we'll start with Faraday's law, which reads that epsilon, our EMF, is equal to the negative time derivative of our magnetic field with respect to time. Rewriting our magnetic field equation from our problem statement, 2.00 e to the negative 3t sine of 120 pi t. You'll notice that this function is effectively two separate functions multiplied by each other, this exponential term as well as this sine term. In order to find the derivative of this function, we will need to apply the product rule. Again, noting that these are in units of milliwebers. So, time derivative of our function, first times the derivative of the second, we'll just rewrite the first one off the bat, e to the negative 3t. Derivative of sine is cosine, and according to the chain rule, we'll also have to multiply by the derivative of this interior portion, 120 pi. So times 120 pi cosine of 120 pi t for the first half, and then plus the second function times the derivative of our first. Derivative of our first being the derivative of the exponent times the coefficient out front, negative 6 e to the negative 3t, and then just times our second function, sine of 120 pi t. It's helpful to take note of what the units on our derivative function would be. If our original function was in milliwebers and we're deriving with respect to time, then our units for our derivative function will be milliwebers per second. And as a Weber per second is equal to a volt, this will be equivalent to millivolts, which is good. That's what we're looking for, induced EMF. Powered with this expression for the derivative, we will actually first combine like terms. Equals 240, and just clean this up a bit. Cosine of 120 pi t minus 6 e to the negative 3t sine of 120 pi t, again in units of millivolts. In order to find the instantaneous rate of change of our magnetic field at our relevant time intervals, we'll need to substitute each point in time wherever we see t in our derivative function. Let's start with a first. T1 is equal to 0 seconds. So we'll be plugging in 0 seconds everywhere we see t in our function. Negative 3 by 0 is 0, and anything to the 0 power is simply 1. So that evaluates to just 1. 120 pi 0 is 0 as well. Cosine of 0 is 1. So we have 1 times 1 is equal to 240. I left out a pi here. Our left term will evaluate to simply 240 pi. Looking at the right term, 3 by 0 again is 0. E to the 0 is 1. 120 pi 0 is 0. Sine of 0 is 0. So our entire right term will actually evaluate out to 0. Minus 0. Solving for 240 pi will give us about 754 millivolts, which actually is our induced EMF. Knowing the induced voltage, we'll be able to apply Ohm's law to solve for the current. 754 millivolts is equal to I1 times the resistance we have here, 5.0 ohms, gives us I1 is about 150 milliamps. Great. We have the magnitude of our induced current. We then need to find the direction of the induced current relevant to the flow through this resistor. In order to do that, we'll lean on Lenz's law, which reads that the direction of the induced EMF opposes the change in the magnetic field. Since our change in magnetic field at time t equals 0 is positive, meaning that is increasing up out of the page, our induced EMF will oppose that and go into the page. Applying the second right-hand rule, we're going to grip our circuit with our fingers curling in the direction of the induced EMF, so into the page. Our thumb will direct us where our induced current is going, resulting in a clockwise flow to our induced current. Following our circuit around, that would imply our current would flow downward through our resistor. And we'll have two more chances to interpret that as well. And that is A. So let's do the same thing for a separate point in time. Point B, time 2 is equal to 2.17 times 10 to the negative 2 seconds shortly after A. So substituting that in, evaluating this, came prepared, so I'll be able to simplify this. Go ahead and perform this calculation on your own if you need to convince yourself. Our left term simplifies to approximately negative 227 millivolts. And we're going to subtract from that this negative term gets us minus 5.32 millivolts. Which simplifies to 232, negative 232 millivolts. Great, so we'll apply Ohm's law again here. We're going to disregard the negative sign, just concerning ourselves with the magnitude of our current. So we'll have 232 millivolts is equal to I2 times our resistance, which is again 5 ohms. We will solve that I2 is approximately 46 milliamps. Awesome. We'll apply Lenz's law again. However, the only difference is our change in magnetic field is actually negative this time. So our change in magnetic field is decreasing going into the page. Thus, our induced EMF will be upward coming out of the page. Applying second right-hand rule again, we're going to grasp our circuit with our fingers curling towards the direction of that EMF change upwards. Our induced current is to the right, implying a counterclockwise flow. Falling around would imply our current is traveling upwards through our resistor. And that is part B. Let's do it one last time. Part C is quite some time later, relatively, of 3 seconds. Substitute that in to our rate of change of magnetic flux function. Solving for this, again, go ahead and convince yourself by doing it on your own. We get 9.30 times 10 to the negative 2 millivolts. And our right term simplifies out to 0. Again, because 120 pi times 3 will evaluate, the sine of 120 pi times 3 will evaluate to 0, canceling out that right term. That gives us 9.30 millivolts. Perfect. Let's apply Ohm's law again. Is equal to I3 times our resistance, 5.0 ohms. We get a magnitude of our induced current to be quite small. We'll get 1.86 times 10 to the negative 2 milliamps. Now to check for the direction, our d phi dt, albeit small, is still positive. So our increased B will result in an induced EMF downward into the page. Second right-hand rule, curling into the direction of that induced EMF. Our induced current will be out to the left, resulting in a clockwise rotation of our circuit, which following around will lead again to a current flow downward through our resistor. Downward through R. There we have it. A, B, and C. We have a magnitude and direction for current through our resistor induced by changes in our applied magnetic field. I hope this helped. If you have any further questions, feel free to leave them down below in the comments section. Otherwise, I will see you next time and good luck with your studies. Thanks.